In this lecture, we're going to start with discussing an example from the method of Lagrange multipliers. Now, we've discussed this in lectures. This is more of a summary, a little mini revision type problem that actually comes from your tutorial pack. Okay? Now, before we get to the actual question or the example, let's just remind ourselves about the motivation for Lagrange multipliers. Lagrange multipliers, the method involved is very useful when you want to maximize or minimize something subject to a condition or a constraint. And these kinds of problems crop up in all sorts of applied areas from engineering and science and physics. Okay, and I've listed a basic problem here where you've got to design a silo, a cylindrical silo, to maximize its volume subject to some fixed amount of building material. Okay, so let's have a look at the following problem. Suppose we have a metal plate that's set in the xy plane and it covers the set omega. Now, suppose that at each point in that disk or that plate, you have a temperature associated with each point. What we're asked to do is to determine the highest and the lowest temperatures along the boundary or the edge of the plate. So we're not concerned really with what's going on in the interior. We're just interested in what's happening on the boundary, the edge of the plate. So this is a problem that we can solve using Lagrange multipliers. You can use other methods, but I'm going to show you how you can use Lagrange multipliers for this one. So let's write it in the terms, I guess in Lagrange multipliers context. Okay, so we wish to maximize and minimize the temperature function subject to a constraint equation. Now, think about what equation the boundary would represent of the disk. Well, it would just be a circle with radius 5 and center at the origin. Okay, so essentially we want x squared plus y squared equals 5 squared. So this is how we form our constraint equation. Okay, now we usually just write g equals 0 for convenience, or historically that's the way we do it. Okay, so how do we do it? Well, the Lagrange multipliers method relies on the following fact. Well, the points where f has local extrema subject to the constraint g equals 0 must satisfy the following. Okay, so remember the gradient, that little triangle, triangle f, is just a vector with partial derivatives of f as the components. So df dx, comma, df dy, df dz. Okay, well, you could write out these equations, but we've been solving these problems in the context of critical points. Okay, so I'm going to introduce the Lagrangian function and then calculate the critical points of the Lagrangian function. It's equivalent to solving this problem here. Okay. So let L be f minus lambda g. To solve this, we just compute the critical points. Of L. Okay, so let's differentiate this, calculate the partial derivatives, right? So we're going to solve, okay, what's that going to be? Well, f minus lambda g, it's that minus lambda bracket that. So I'm going to get 8x minus 4y, then I'm going to have a lambda in there. So when I differentiate that with respect to x, I'm going to get something like minus 2 lambda x. Okay? Now let's compute dl dy and set that equal to 0. Okay, so let's just differentiate this with respect to x and this with respect to x, y, and this with respect to y, and then set it equal to 0. So dl dy is going to be something like minus 4x plus 2y, and then when I differentiate this with this as my g, I'm going to get a minus 2 lambda y equals 0. Okay, so there's two equations. Remember, I've still got my other equation, g equals 0, up here. Okay, so I've really got three equations and three unknowns. G equals 0, this, and this. So, let's call the constraint equation, let's call it C. Okay, so now what we would like to do is somehow solve 1 and 2. Well, I can eliminate these terms here just by adding 2 times this equation to this equation. Okay? So consider equation 1 plus 2 times equation 2. Okay, when I add those in together, the first 2 terms are going to cancel out. And it's going to give me the following. Okay, so multiply that by 2 and add those 2 together. Okay, so from that equation, what can I determine? Well, I can factor out, say, a minus 2 lambda. And get something like this. Now, this is a good situation to be in, because I know that either lambda is 0 or x equals minus 2y. So that's information that I can work with now. Okay, so what we're going to do is discuss those cases separately, right? We'll discuss the case lambda equals 0 separately, and we'll discuss the case x equals minus 2y separately. Okay, so let's do that. Okay, so what will happen? If lambda equals 0, let's just go up to equation 1. If lambda is 0, then that term's going to disappear. So I can come up with something like y equals 2x. Yes? So what can I do now? Well, what I'm going to do is use the constraint equation. So I can go up to my constraint equation, equation 3, and replace y with 2x. So let's replace y with 2x in the constraint equation to form the following. Okay, so essentially we're going to get something like 4x squared there, and just add those together. So we're going to get 5x squared equals 25. Thus, so if I rearrange that, I'm going to get plus or minus root 5. Okay, so what are the corresponding y components of our point? Well, if x equals positive root 5, I can go in here, and y will equal 2 times positive root 5. If x equals negative root 5, then I'll get negative 2 times root 5. Okay, so just from there. Okay, so for this case, for the case lambda equals 0, our points of interest are, now the positive refers to, and the positive sort of are together here, so we're not mixing up signs. Okay, so that's 2 points of interest, but we've only discussed one case. We've only discussed the case lambda equals 0. We still haven't discussed the case x equals minus 2y. Okay, we've done this case, but let's discuss this case as well. Okay, so in the case x equals minus 2y, well, we're going to use the constraint equation again. We're going to use the C equation, the x squared plus y squared equals 25. We're just going to substitute the x out. So similarly, C yields the following. Well, we're going to replace x with minus 2y squared, so that's going to come to a 4y squared, so we're going to get something very similar to the previous case. Okay, well, if y equals positive negative root 5, then I can get x from here. But the signs will be different because we're multiplying by negative 2 here. So it's going to be negative positive 2 root 5. So our points of interest for the case x equals minus 2y are the following. So the signs are mixed. Okay, so anyone remember what we can do now? We've got four points. What do we do with them? Yeah, just let's compare the values of the temperature at each of those 4 points. Okay? Remember, we're looking for the maximum temperatures on the boundary and the minimum temperatures on the boundary. Okay, so we want to find the temperature at each of these points and then compare the temperature values. Okay? So, compare values of F let's compare F at this point, this point, this point, and this point. All right. Now, our F is just here. So let's plug in and see what we get. So if I plug in this point, I should get something like 0. I'll let you do the calculations for this one. Similarly, if I plug in this point here, because I've got squareds involved, I'm actually going to get the same answer. If I plug in the case when x equals minus 2y, okay, if I work that out, I get 125. And similarly, when I plug in negative, if I mix up the signs, I also get 125. So, the question is, which ones lead to a maximum, which ones lead to a minimum? Well, obviously these are mins, and these will be maxes. So, there are 2 points on the edge of the plate where that has the lowest, these are the points, and the lowest temperature is actually 0. Similarly, at these points, the temperature function is a maximum. Okay? Now, if we want to maximize or minimize a function subject to a condition, a constraint, then the process I've used is to define this Lagrangian function and then calculate the critical points. Now, in this case, our function had more than one critical point. And what we did was we compared the values of the function at each critical point. And then we just chose the ones that we wanted. So here's an example for you to try. Here's a function xy subject to this constraint here. So this is a plane. Determine the maximum value of this function subject to this constraint.